So now we are online, we can say, and we can start sharing the screen and discuss about the phenomenon of interaction in linear regression. So previous examples for linear regression were using one independent variable. We call this case as simple regression, or more than one independent variables, and we call this case as multiple regression. We didn't still somehow combine two or more variables into one variable. And this combination of more than one variable together is called interaction. So interaction means that I combine mathematically, I'm multiplying values of original variables, and I am creating new variable, which is called interaction. So if we like to discuss about these interactions, so maybe we should give some reasons why we should add interaction into our discussion. So I will give you some insight before we start computation by two pictures that were added to this presentation. That's why this presentation is called Updated. And then we will try to compute results which are present on these pictures. So first of all, let's start with our previous example. And the example was that we added a variable of size of the flat and whether it is new or not. And if you apply this model, I would call it model with no interaction or without interaction. So I would get this green line, which would be a line describing relationships for flats in old houses. So it means that intercept or constant would be approximately 890,000, and increase by 1 square meter would be approximately 14,000. And if you compute result for variable new, which is describing new flats, you would add this added value approximately 500,000. So it means that all flats that are new according to this model with no interaction are more expensive by approximately 500,000. So this blue line is describing this phenomenon, and these two lines, as you can see, this green line and blue line, are parallel. So it means they have the same shape. So it means that this increase by square meter for new flat is the same as the increase for old flats. But maybe that this model is unreal. What can be unreal in this model? What should be improved in this model? That's the question for you. What can be improved in this model? Should be the price per square meter the same for old and new flats or not, according to your expectation? Please try some answers.
There are more variables that come into play. So, you know, like such as if it has balcony, if it's reconstructed or not. So, yes.
Now we are discussing only about the difference between flats in new and old buildings.
Oh, okay.
We are discussing whether this is real picture, that price of the square meter would be the same for both of these different groups of flats, but only there will be a shift approximately 500,000 in these prices. The question is whether the price per square meter for old and new flat would be the same or not. This is the question what we are discussing about. Would you agree with such statement that these prices of square meter would be the same for old and new flats, or there should be some difference?
No, there will be some difference.
And it means that flats in new buildings should be slightly more expensive? Not?
Yes.
Okay, so I can see your answers also in chat. Okay, so this is picture with included interaction. We will explain more later, but now you can see that this green line and blue line are not parallel, so it means they do not have the same shape. This is slight small increase, and this is quite big increase. It means that price per square meter for old flats is approximately 13 thousandths, and for new flats 13 thousand plus 5,000, it means 18.5 thousandths. So you can see that this picture is maybe more realistic and describing our situation, that for new flats the price per square meter would be different. And this is how interaction works by pictures. We will go back to this picture in a few minutes, and now we will try to compute our results. So I would go back into JASP. And here, before we start to model interactions, we will only try to compute the same model as we have here. So it means only size, price, and whether it is new or not will be included. So I would call for new regression, linear regression, of course, and we will add our variables. So price is dependent. Size, which is centered, would be the first independent, and the second independent variable would be new. So here it is. I will only ask for some more results, so into statistics, and I would ask for confidence intervals. And I hope that we can see results at the end. So here it is, and here we can see our results. I hope so. So maybe we will slightly correct our results in slides that were prepared only by my expectation. So Intercept is currently it is correct. So Intercept is 875. So here it is 890. So I will slightly correct it. 875,000. C size is 3.7. So I will make a small change, and new is approximately 490,000. So now this picture is correct. And this is picture with no interaction, only including C size, new, and intercept. So intercept is here. The value of slope for variable new is added intercept for new flats. And the last one, coefficient, it is the slope for C size, is present here. So it is the average size per square meter for old and new flats. Once again, this model is not realistic, and that's why we would add interaction. So it means we would take variable of size and variable with this, whether it is old and new together, and we will create new one variable. There are two options in JASP how to create interactions. First option would be to go back to our data matrix and click on this black plus and compute new variable, which is multiplication of C size and whether the flat is new or not. Fortunately, JASP can prepare interactions also by easy way, so it's not necessary to go back into data matrix and to create multiplication. So I will make only the note for this model. So I would call it that this multiple reg without interaction. now I will make a copy. And I will change title and I would type that I would create multiple regression with interaction. So now it is prepared. And if you would like to prepare interaction, so that's quite easy in chess. You would visit the option which is called model. And here you can see that you can take both of these variables. So if you click on the left button of your mouse, then click onto Control on your keyboard and New as the second one by left button. So you will take both of these. And if you move two variables advanced by this arrow, you would create interaction. So it is multiplication of these two variables. So here it is. And now let's go to our results. So we added new one variable, which is called interaction. So it means multiplication of previous variables that were entered into our model. And here we can see our results. So I would go to this picture and I will slightly maybe change these figures that were only approximate. So 875 approximately is the intercept. So here it is. Whether it is new or not, 385. So I would add 385 to be correct. Then C size approximately 13.5, so that's correct. And C size new plus 5,000, so it seems correct. Okay, so before we start to read picture, we would try to interpret these results. So first of all, we would discuss about the value of the intercept. Can somebody help me and try to interpret what is the meaning of intercept in this model with interaction? For which flats this is the price? 875 crowns, 1,000 crowns approximately. What could be correct interpretation?
The new one?
No. Once again, let's go back to previous lectures, and we discussed, I hope repeatedly, that the intercept is the value for those units that have zeros for the rest of variables. So which flat is described by zeros for C size new and C size multiplied by new? So C size is once again centered size of the flat. So it means that the average flat has zero for this variable C size. New is coded as 0. The flat is not new, it is old. And 1, it is new. And C size multiplied by new is only multiplication for these two. So what is the meaning of the intercept currently?
It's a price for an average sized flat.
Old or new?
Old.
Yeah, S. C size is 0 for average size, new is 0 for old, and C size multiplied by a new is 0 for average size flat, which is not new. So that's correct. So this is the meaning of the intercept. Let's go to the interpretation of this C size coefficient. So what is the slope for C size? It is the average price per square meter for new or old flat?
Old flat.
Old flat. As for new flat, we should add also this value of the interaction. Okay, what is the meaning of the slope for this variable new?
That's a price we add to the flat if it's new.
Generally Or if we would like to be even more precise, if we take the price of old flat, which is of average size, so it means this value, so average flat, which is new, for this we must add this constant. So intercept for new flat will be this value plus this value. Okay, and C size multiplied by new is added value per square meter to this coefficient for C size. So it means that the slope for new flat would be 3.5 thousand plus 5,000. So it means approximately 18.5 thousand. So if I go back to my picture here, it should be even more clear, I hope so, in comparison with previous table. So this is the value of the intercept. The value of the price for the flat, which is of average size. So it means has 0 on x-axis. So this is the intercept. So this first value. Second value, C size, is slope for this green line. So it means line for old flats. Next one, new, is this difference. So it means for flats with average size, you must add for new flats approximately 105,000 Czech crowns. And this is added value for the slope for new flats. So it means not 13.5 thousand, but 13.5 thousand plus 5,000. That's the slope for new flats. So it means the average size for new flats is nearly 1/2 higher than for old flats. So that's results of interaction graphically described on these pictures. Okay. If I go back, we can also discuss about generalization. So it means we try to infer our results from the sample, as this is description for my sample, to the whole population. You know, there are two options in classical statistics. We can discuss about confidence intervals, it means last two columns, and we can discuss about t-test, so we can discuss about t-statistics or p-value. If you try to have a look into these figures, so it means t's, p's, or confidence intervals, the question is whether this picture, so it means the difference for new flats and old flats by slopes, not only by intercepts, is good for my data, or whether this generalization is maybe wrong. So if you like, please try to read these figures of T's, P's, or confidence intervals and try to discuss about possibility to generalize this difference of slopes for old flats and new flats to the whole population. Can we generalize our results or not?
We can't, because the P is too high on the size new column.
So this P value is quite big, or T value is quite low. Confidence interval can be from minus to plus. So maybe that our result, which is descriptive here on this picture, is not realistic for the whole population. Do you have some idea what can be the reason? As the expectation would be clear, I would expect that the price per for new flat would be higher than for old flat. What can be behind this, let's call it non-significant statistical result?
It's possible there are not so many new flats, so
possible.
And also other other values could be more descriptive about the price of the flat.
Okay, thanks a lot. I would currently try to make a picture for the variable nu. So if I can see the mean for this variable is 0.02, so only 2% of new flats in my data file. I'm still waiting for frequency table. Oh, it's not present. Sorry for variables that are not cardinal, so it wouldn't show this picture. But if I remember well, there are approximately 5, 6 U flats, or maybe 7 in my data, and that's why my result is not very reliable, and that's why I cannot generalize this result about interaction to the whole population. So that's only a final result. So I would close this dialogue, this presentation, lecture 2, and I will open the next one, presentation number 3. So here it is. And we will move forward to the discussion about problems in linear regression model, and we will learn how to find problems in our model and how we can solve these models problems. So here it is, so I can open the dialog and close it. So here it is. So I would go to the second slide and we will discuss only some problems that can be present in real life linear regression models, but I hope that these problems are the most important, so you would have idea about classical discussion in linear regression. So first of all, we have covered previously some brief discussion about the problem of influentials and outliers. I guess that you remember that if we go back into our data file, you are able to find some special flat with some big size. Here it is. It is the row number 155. And it was the flat which price was approximately 3 million Czech crowns, but the size was approximately 440 square meters. And we excluded this file as if you introduced this flat into our computation, correlation would be biased, regression would be biased, etc., etc. So this is classical example of so-called influential and outlier. So it means one value at least is extreme, so it is outlier. Here, what is outlying is the size of the flat, 440 square meters. All the rest flats are below 200. And it is also influential. It means that if we add this flat into our computation and if we exclude this flat into our computation, the results would be totally different. So that's discussion about influentials. So at least we know something about these influentials, and today we will learn only more how we can find automatically. It means by some diagnostic checks in JESP influentials, and we will discuss also about the possibility of solutions. So next two problems are somehow related. These are called as heteroskedasticity and autocorrelation. And these two problems are related to the random error. So it means whether the regression line is following our points ideally. So if I go back, I guess we have here some pictures from previous lectures. Yeah, here it is. So here you can see that our points are quite still in the same distance from this line, and this model That's why maybe would be called as homoskedastic. So it means that the variance is nearly all the same around the value of independent variable. Opposite case would be that these values, for example, would be very close to the line here and very far here, and this would be a picture of so-called heteroskedasticity. The second problem, which is closely related to the heteroskedasticity, it means through some differences in individual points from the regression line, is called autocorrelation. If my data are called as time series, it means I repeatedly observe the same observation in time, and the values from previous points are somehow related to observations in current time, there is something what is called autocorrelation. So it means it is a relationship in individual time points, and also this problem must be solved if it is present in regression linear model. Last problem we will cover in detail, as it is nearly every time present in real data, is called multiculinarity. As ideal case would be that our independent variables, for example, last model included C size and whether the flat is new or not. So ideal case would be that these two independent variables would be totally independent to each other. So it means if you compute, for example, C size and new correlation, ideally it would be 0. But we are not living in ideal conditions, especially in social science. So that's why usually two or more independent variables are somehow related. And if they are related, we are discussing about multiculinarity. And if this relationship is very strong, it will influence our results. So that will be discussion about multiculinarity. And before we start to discuss individual problems, we will cover influentials and outliers, heteroskedasticity. As we are not discussing about time series, I will only mention some basics about autocorrelation. And in detail, we will cover also multiculinarity. Before we start, we need to know some more details about residuals, as these residuals are usually base for computation of these problems. So, before I start to discuss by presentation, I would only repeat the basic idea. So here I have combinations of real data. So these are these gray circles, and this is our regression line. I would like to repeat that this regression line in most statistical packages is designed by so-called ordinary least square techniques. And this ordinary least square techniques is based on this idea. I would take the difference on vertical axis between the point and our regression line, and this difference between real height of the point and height on the regression line is called residual. So this difference is one residual, this is second, the third one, fourth one, fifth one, etc., etc. For this case, as we have 262 flats, we could compute 262 residuals. These are residuals. It means something that can be found in my real data in my sample. I guess that you know from previous lectures that for the whole population, we are describing not residuals, but for the population, we used Greek symbol epsilon, and we describe these epsilons as so-called random error. So in population, we have random error, and for real life data from sample, we have something that is called residual. So I would call it that residuals are something like empirical mirror for population random errors. So that's the relationship between residuals and random errors. For random errors, so it means values that are somehow differentiating real data from the model. There are some expectations. As these expectations should be followed if your results are correct, so we must discuss about individual diagnostic instruments that can help you to find it. So now short excursus about residuals, about different types of residuals that can be computed for analytical description, whether my model is good or not. So first of all, we can discuss about so-called unstandardized residuals. So it means it is only the difference between real value and between the value which is modeled by this line. Here, this is the second unstandardized residual, the third one, fourth one, etc., etc. So these are called unstandardized residuals. If you would like to show some equations, so they are usually called as small e's. So it is similar to big epsilons for population, and it is the difference between real value and value which is modeled by my regression line. Usually we use this y hat symbol for this model value. So difference between real value and value on the line. They can be computed for these residuals. We can compute also variance by these equations, etc. We will not go into details. Sometimes it is recommended if you are computing residuals not to compute directly for this line that is computed for all data, but it is recommendation that we can compute so-called predicted residuals. These predicted residuals are based on this idea. I would take this point, but this line would be computed if I exclude this point from the computation. So that's why in this equation there is symbol ey minus y. So it means this last observation is missing in the computation. So that's so-called predicted residuals. Not all software packages can compute these predicted residuals, but according to theoretical equations and also by practical simulations, it seems that these predicted residuals are better for finding problems in real-life data. If we would like to work with residuals, we must somehow change the original scale, as original scale of standardized residuals would follow the scale of dependent variables. So for example, here it would follow the prices of flats. And these residuals in original scales cannot be tested statistically. They do not follow any well-known statistical distribution. So that's why we are somehow preparing different versions of so-called standardized residuals or jackknife residuals. So this is nearly the same, only for standardized residuals we are computing with original unstandardized residuals. And for so-called jackknife residuals, we are using standard error for these predicted residuals. So that's the difference. So there are many different ways how we can standardize residuals. And for these standardized residuals, we can then use testing as these standardized or jackknife residuals or different kind of standardization usually follow standardized normal distribution. So we know, for example, that only approximately 5% of these residuals should be outside the range -2 and +2. So that's the reason why we are computing standardized residuals. And now let's skip from residuals briefly to the first problem of so-called influentials. So if we have some strange points in my data that can somehow bias my result, So it means they can change the computation of the slope, of the intercept, or more slopes if there are more than one independent variable. This case should be called as influential. And our analytical goal is, before we start computation, find and exclude these influentials, as we would like to have our results not influenced by these special cases. There are two possibilities how we can find influentials. If we are describing only simple regression model, as we have here, we can use this picture. So it means this scatter plot of independent and dependent variable. But if we are discussing about multiple regression, it's usually useless strategy, as influential can be some extreme point, it means big or small in some dimension, but influential can be also some special combination of independence, and it is impossible to find it by description of extreme values. So that's why we usually use another diagnostic tools, and we will briefly cover these tools in the next two slides. So well-known procedures for detecting influentials are called DfBetas and DfFits. Here is description how it works. So the logic of DfBetas and DfFits is very, very close to previous discussion of so-called predicted or deleted residuals. So I would, for example, take this point and I would compute regression this point and without this point, and I will compare the individual slopes for independent variables, or I will compare individual lines for these points. So that's why we call DfBetas. It is difference between slope and slope if I am not including this point into the computation. And DfFits are the similar topic for so-called DfFit. I'm computing difference between estimated value of dependent variable. The problem is that DfBetas as well as DfFits doesn't follow, once again, any well-known distribution, and usually follow the scale of original dependent or independent variables. So that's why there are some special formulas for computing something what could be called as standardized DfBetas or standardized DfFits. These are called usually NDfBetas or NDfFits. Unfortunately, JESP or M+ we are using in this course are not capable of these DfBetas or DfFits or even their standardized versions. So that's why we would finish this discussion very quickly. Here you have a recommendation if you are using standardized DfBeta. So the limit that shouldn't be exceeded is based on the rule 2 divided by square root of number of units in your sample. And for DfFits, a similar rule is applied, 2 divided by square root, but here the fraction of your sample size and number of predictors plus constant. So that's DfBetas and DfFits or their standardized versions. In JESP, we have only one, but it is still quite good strategy how we can detect influentials, and it is called Coop Distance. So this Coop Distance can be found if we go back into our previous example. So I guess here in statistics, we can find Coop Distance. So here it is, residuals, case-wise diagnostics, and here you can see Coop's distance. So here it is. By default, JESP is using the table. Here it is. This is the table of case-wise diagnostics with Coop's distance over 1. So there is quite a famous recommendation in the literature that if Coop's distance is over 1, it means we have some influential in my data. Fortunately, if we excluded this special big flat, there is no more any other influential in my data. This table is blank, so there is no case. You can try, but I wouldn't run this once again to change filter in your original data. So it means once again include this case into the computation, and I guess that you would find that for this flat, which has case number 155, there would be some value which would be above 1. So it would be included in this table. I wouldn't run it as JESP should recompute all these results, and it would take at least minutes. So I wouldn't start this procedure, but you can try it and you can find that for this point, we excluded previously from our computation, we would find Coop Distance, which would be, I guess, approximately 25 or some big value. Last discussion about influentials should be what we can perform if we find influentials. So especially if you are interested in the relationships, so it means in individual coefficients between independence and dependent variable, so we should omit influentials from my data. So it means in the same style as we excluded this value, we should exclude all other values that can be influentials and then recompute our model. So this is practical recommendation related to influentials. So, are there any questions so far related to influentials and diagnosis on influentials? Okay, so if there are no questions still, so I would go back, and the next topic we will try to cover is called heteroskedasticity. Once again, the assumption for classical regression model related to random error. Once again, random error is present for the population data. For our sample data, the same phenomenon is residual. An assumption for random error is that this random error is all the same in the size for small as well as big values of independent variable. So it means that the variance of random error is constant across the values of independent variables. There are more possibilities how we can recognize whether heteroskedasticity is present in my data or not. First, and I would call it maybe the simplest, or at least it seems it is the simplest way for detecting heteroskedasticity is to see some special pictures, some special charts for residuals. Usually you would make a picture of residuals versus independent variables. If we try to prepare some pictures in JESP, I guess it's not too difficult. So you would visit the last section, which is called plots. And here there is at least option of plots, residuals versus covariates. This is the second type of plots that are present here. So I would prepare these plots. Only before JESP will prepare these plots for me, I would add comment that these charts also do not have any meaning for variables that are binary. So it means for variable new and old flat, we will not inquire this picture. But here we can see at least for this variable C size, that it seems slightly that the variance, so it means this picture, is increasing and increasing as size is increasing. So it seems maybe there is also a problem in my data called heteroskedasticity, as you can see that points here at the beginning are quite close to this line. And if you go up and up, it means increasing size of the flat, these values are bigger and bigger and far from this line. You can see also on this picture that these are residuals that are unstandardized, so it means in original values, so it means original prices, estimated by my model, and real price is different. And here you can see the scale of standardized residuals. So you can also see that if you take the range -2 and +2, so at least here there are quite some big strange points. It means values with big standardized residuals. If you go back into our discussion about residuals, and then we would go back once again into heteroskedasticity. So in statistics, you can also ask cases with big standardized residuals. This is the same style as finding influentials. So I would close this dialogue, and we would go back to this graphical diagnostics. And it seems, at least according to my analytical experience, that in my data there is maybe heteroskedasticity present, and it is related to this variable C size. We should discuss briefly about consequences of heteroskedasticity in my data. So if my data are following this picture, or another options that can be present in heteroskedasticity patterns, it can be that my standard errors for individual coefficients are bigger than they should be if there is no heteroskedasticity at all. So it means that if I go back into my results, so this column is maybe biased and biased upwards. And if this column is somehow biased upwards, so it means these values are bigger than they should be, it means also that this value divided by this value, it means T ratio, should be lower. And maybe it also means that P values would be higher. And also it means that confidence intervals are broader than they should be. So this is the influence of heteroskedasticity. So it means it can happen that our tests are statistically insignificant, not as we have small sample, as we have unreliable data, but we have heteroskedasticity in my data. And last, what we would cover in this heteroskedasticity excursus, we would discuss about possibility how to test heteroskedasticity directly in my real life data. There are at least two options, and different software packages offer different testing strategies, but two well-known tests are called Glazers and Goldfeld Quant test. We would discuss only about Glazer test, as it is the easiest way for implementation in JASP. If you would be using some special packages that would offer another testing procedures, of course, feel free to use another tests. So first of all, let's go to Glazer's test implementation in JASP. So what is the logic of this Glazer's test? So first of all, Glazer recommended flowing. So let's take these differences of these residuals. It means these vertical points, or if we go back into our previous picture, so these are these sizes. So these are residuals. So it means let's compute these differences. And according to Glazer, it is recommended to take absolute values for these differences. So you would take this value, this plus, and this value, which is minus, would be after absolute value also plus value. So you would take absolute values of these residuals, and you would prepare the model in which original independence, so it means, for example, C size, nu, etc., would be once again independent variables. So your dependent variable would be absolute values of residuals, and your independence would be the same as for original regression model. And then you would evaluate this regression model, and if some independent variable would be related to the absolute values of residuals, there is heteroskedasticity. if none of independence would be related to absolute values of residuals, there is no heteroskedasticity and no problem at all. So now we would show how it works in JESP environment. So it means we would try to implement this Glaser test into JESP. I would propose for simplicity to go back to previous model with no interaction, as maybe this model is better for my data. So here is the table with our coefficients. So I would maybe make a copy of this table and include it here on this PowerPoint slide. I will try it. It should work. I hope so. Yeah, it seems it works. So I would only make bigger figures for the values that we would need. So maybe I can erase all these. Okay, so maybe I would only erase this one and move it upwards. So erase everything what's not necessary. Have the values available for me. Here it is. Okay. And we would need at least these values to be bigger to see these values. So it's too much. So okay. So now it seems we are able at least to read these values. So first of all, what we would need in JESP is that we would need to add new column which would be including residuals. So it means, once again, it would be the value of original price of the flat, once again, original price of the flat and price of the flat defined by my model. So it means I would take this intercept plus C size plus new and I would compute the real value expected by my model, and I can subtract this value from real price, which is present in the first column. So I would compute price minus intercept C size coefficient multiplied by real value of C size plus new multiplied by this coefficient for new variable. So that's why I need these figures. That's why I copied these into PowerPoint presentation. So first of all, I'm computing residuals. Unfortunately, JESP cannot do it automatically, so I must use this computing column. So I would call it as res instead of residuals. It would be scale variable, and I can create column. So I would start typing. Maybe I can start first of all to say that I would take price. So I would click onto this price. I would take minus. Then I need to take the intercept. So I would copy the value. So it is 874,553.761. If you like, you can round up slightly. So that's constant, subtracted for original price. Then I would take, once again, minus, as I need to subtract also the C size value, multiplied by size. And I need also, oh, no, it's not correct. So once again, so maybe first of all, I would compute only the result for estimation. Sorry for that. I would take, first of all, this C size multiplied by this value. Then I will add plus. No, I don't need brackets. So once again, plus. I would take new multiplied by coefficients for the new. I would take also plus constant intercept, which is here. I don't know why JESP is including these strange. Oh, that's not correct. So once again, I will try to erase this one. And once again, so I would like to get C size multiplied by coefficient. So this is coefficients for C size. Then I would like to add, it's not working, sorry for that. I don't know why is it so, as I'm not implementing usually these formulas in JESP. So I will try to prepare you a special video for this, sorry for that. But what would be the result? I would take it quickly. I would compute these residuals, I would make absolute values, and I would compute regression for this. So that's the meaning of this test, which is called Glaser test. And then you would evaluate this test. If heteroskedasticity is present in your data, there is an analytical solution which is called weighted least squares. So it means that if you go back and you find some special points that are influencing your results quite a lot, so it means with big residuals. So it means these points, for example, here on this picture. So you would take the weight of these points with big residuals only as a small weight, and points that are close to the line would have higher weights. If you would like to implement it, but it is quite complicated in JESP, you can go into regression procedure, and there is, I guess, yeah, here it is, there is special window for this weighting variable. So this is weighted least square techniques, which is usually applied for some big heteroskedasticity problems. Okay, and last one problem we will cover is called multiculinarity. And this problem is if there is strong relationship between independent variables. If there is strong relationship between independent variables, it means that once again, standard errors of coefficients are inflated. So this is nearly the same problem as for heteroskedasticity. T-test would be statistically insignificant, and maybe even bigger problem for multicollinearity is that estimates of individual coefficients, so it means these values for this first column can be biased. Even sometimes they can be totally reversed, so it means from positive negative values are vice versa. So as this problem of multicollinearity is quite often present in my data, so there are quite developed techniques how to detect these problems, and also we will discuss about solutions for these problems. So if we would like to have very simple tool how to detect multicollinearity, but we will not compute it, you can compute correlation coefficient for all independent variables, and a recommendation is that if these values, at least one of these values, is above 0.8, excuse me, so there can be problem. But we will cover some maybe slightly advanced options that are called tolerance, VIF, and conditional index. All of these are present in chess as well as in other classical statistical packages, so that's why we will discuss about these. So first of all, brief description of these tools. So tolerance means that I would take one independent variable. For example, in my case, I would take new variable, and I would compute regression for new variable as dependent and C size as independent. And I would compute R squared, it means coefficient of determination for this regression. And 1 minus this R squared is called tolerance. And reversed value, so it means 1 divided by tolerance, is called VIF. Recommendations related to tolerances and VIFs are following. If the tolerance is below 0.2, some people also say only below 0.1. So there is big problem in your data, there is big multicollinearity, and you should try to solve it. For VIF, as it is only the reverse value, so it means instead of below 0.2 or 0.1, values above 5 or above 10 are problematic. So that's tolerance and VIF. And let's show how it works in CHESP. So once again, I would go back to multiple regression without interaction case. So it means only C size and nu is included, no interaction is included. So it means it was the best model we have covered today. So I would go here into statistics section. And the last one option on the right-hand side is called Coronarity Diagnostics. If I click into this section, I would get new one table, which is called Coronarity Diagnostics. We will discuss about this in a few minutes. But for classical coefficients table, I would add 2 new columns, which is called tolerance and VIF. Once again, tolerance means 1 minus R squared for regression between these two variables. It means C size and nu, and VIF is only reversed value. So if I check these values, 0.972 for all, it is the same as, of course, if I have only 2 variables, explanation of the first one by the second one must be the same as explanation of the second one by the first one. So once again, recommendation is if the value would be below 0.2 or 0.1, it would be problematic. Here, there is no problem at all. And for VIF, once again, it is only 1 divided the tolerance. So it means 1 divided 0.972 is 0.25. And once again, recommendation values above 5 or 10 are problematic. So once again, no problem at all. If you are using tolerances, you don't need to use VIFs, or if you are using VIFs, there is no need to use tolerance, as these are related indexes. So that's about tolerance and VIF. And the last one option we should cover by multicollinearity diagnostic is conditional index. And it is based on computation in this next table, which is called Coronarity Diagnostics. And this conditional index is based on computation of ratio between these eigenvalues. So it means it is computing ratios for these values that are called eigenvalues. And if we try to evaluate multicollinearity by this only one figure for the whole regression model, we would go into the last column. It means we would compute max divided by minimum. So it means this value divided by this value. And this ratio can be found here, and it is called conditional index. And this last value shouldn't exceed 30. That's once again recommendation. We usually call these recommendations as rules of thumbs. That's why I'm using here shortage ROT. So that's a recommendation that this value shouldn't be above 30. So that's diagnostics of multicollinearity. So no multicollinearity is present in my data. And if I go back, if there is some multicollinearity, there are following solutions. You can very easily ignore this problem, but then, of course, your coefficients can be totally biased and your results are totally unreliable. You can, and this is maybe the simplest solution, leave out one variable which is related to the rest. There is also theoretical recommendation by statisticians. Try to get more data. Maybe it will solve your problem. Usually social scientists are not allowed to get more data, so this is a really impractical recommendation. Another solution, and we will learn how to perform such solution in some of next lectures, is that we can apply factor analysis to related variables, and we can use the solution of this factor analysis. And the most advanced and sophisticated solution to multicollinearity problem is called ridge regression. Ridge regression is based on a very simple trick that you would slightly change original formula for computation of regression estimates. So you wouldn't take only transposed matrix multiplied by matrix of independence, but you would add only small constant to the diagonal of this matrix. So that's why there is k multiplied by matrix with units on diagonal. And by this small bias of original results, you would get results that will be quite robust to the problem of multicollinearity. There is no special option for ridge regression in JESP, so I guess that in JESP it wouldn't be possible to compute. But for example, if you are using SPSS, so if you download SPSS statistical package, so one of file that is downloaded with the full version of SPSS is also the file which is showing how to apply ridge regression in SPSS. Last one slide is only describing briefly the problem of autocorrelation. Once again, the problem which can be present in multiple regression if you are using data which are in time series. So it means that errors in following observations in time are somehow related. There is a special test which is trying to find whether autocorrelation is present in your data. Unfortunately, we do not have here time series data, so we will not apply this test, but I guess it is applied also in JESP. It is called Darwin-Watson test. And once again, if there is autocorrelation in your data, consequence is the same as for heteroskedasticity, so it means big standard errors, t values would be lower, and p-values for t-test would be higher. Once again, solution is the same as for heteroskedasticity, is to apply weighting least square techniques. As usually, social scientists do not use data in time series. We do not need to discuss about this problem a lot. Once again, I would like to apologize that we were not able to implement Glazer's test. I will try to check how it works in JESP to implement residuals easily, and I will prepare for you the video which will show this case as well in the next few days. So now I would stop sharing, I would stop